In this video, we're going to talk about the boiling point of nonpolar organic molecules. So go ahead and determine if the boiling point of ethane right here is higher than the boiling point of pentane. You could draw pentane like that as well, but let me just draw all of it. So which one has the higher boiling point? The answer is that the pentane is going to have the higher boiling point. The reason is because there are more carbon and hydrogen atoms. In pentane you have C5H12, but you have C2H6 in ethane. When you have more atoms in a compound, the molecular weight is going to go up, which means the London dispersion forces are going to also increase, which is going to raise the boiling point. Now let's explain London dispersion forces. So let me redraw these as bond line structures because it's easier to demonstrate it that way. So when you have a liquid mixture, not a mixture, but a liquid solution of one of these, it's not going to be one molecule of ethane or pentane. It's going to be multiple of them next to one another. So it's going to look like this. When you have pentane, the London dispersion forces are going to be interacting like this. But when you only have two carbons, like you do in ethane, it's only going to interact two carbons. So the London dispersion forces are higher, and this interaction that I've drawn in red are called London dispersion forces, and it takes energy to oppose that interaction and cause the molecule to boil. So now let's go through an example where both molecules have the same molecular weight, but they're arranged differently. Which one of these has a higher boiling point? The answer is that, once again, pentane has a higher boiling point. The reason is because as branching increases, the surface area is going to decrease, and that's going to lower the boiling point. And here's why surface area matters when you talk about nonpolar molecules. If you imagine two pentane molecules next to one another, you can see the dispersion forces, London dispersion forces, interacting with one another. And you can see that they can interact with one another pretty easily because they're aligned the same way. However, if I redraw a bond line structure of what I had before, you can see that you don't get as many points of interaction as you did before. So this is going to be harder to break apart than this, and therefore the boiling point of this is going to be higher. And if you want to put a number on that, this is going to be 9.5 Celsius, and this is going to be 36. So now let's talk about haloalkanes. Compare the boiling points of these nonpolar molecules. Which one of these has the highest boiling point, and which one of these has the lowest? So it turns out that iodine has the highest one. It's 72. Well, not really the iodine itself, but the iodoethane does. Bromoethane has 38 degrees. Chloroethane has 12 degrees, and then fluoroethane has negative 38 degrees Celsius. The reason is because of the size of the atoms. So these atoms right here that are attached to the hydrocarbon chain, these are all called halogens, and this is the way they're arranged in the periodic table. The lower down you move, the larger the atom is going to get, and the larger the atom is, the larger the halogen is, the more London dispersion forces you can have. And so if you have halogen size increase, then that increases London dispersion forces, which increases the boiling point.